Hello, welcome to the next part of our unit on magnetism. In this part, we're going to focus on the magnetic force acting on an electric current. And to begin with, we're going to watch this YouTube video from MIT showing a jumping wire. In this video, you can see a battery, a knife switch, which will send the current one way if taken to the left and the other way if taken to the right. There's a long wire and a strong magnet, and the wire passes between the poles of the magnet. When the knife switch goes to the left, the force on the wire is upward. And when the knife switch goes to the right, the force on the wire is downward, causing the setup to collapse. From that video, you can see that a magnet does indeed cause a force on a current carrying wire. We can quantify that force using this formula, ILB sine theta. I is the current in the wire. L is the amount of distance of overlap between the current and the magnetic field. We'll do some examples where I illustrate this in a minute. B is the magnetic field, and sine theta is the angle, again, between the current and the direction of the magnetic field. And just as we saw with the force on a moving charge, if the angle is 0, there is no force, and if the angle is 90 degrees, the force is as big as it's going to get. Sometimes instead of being asked for the force, you are asked for the force per length. That is asking you to calculate F divided by L, and that just equals IB sine theta. The direction of the force on the current carrying wire is determined by right-hand rule C. Right-hand rule C in many ways is a variation of right-hand rule B, but I find it helpful to give it a new name in order to help students keep straight what's happening. For this one, you stick the fingers of your right hand in the direction of the current, then rotate your hand around until you can point your fingers at a 90-degree angle to your palm, and your fingers should then point in the direction of the magnetic field. Your thumb then gets the direction of the force. So the force on this wire would be downward toward the bottom of the page. Please remember that in the last part of this unit, I go through many examples of using the right-hand rules, and for more details on this, I'm going to refer you to that part. Let's begin with this example. We have a wire carrying 5 amps of current moving in a region of space with a 6 Tesla magnetic field, and we're told that that region of space is 0.4 meters long. Using the right-hand rule, the force on this wire will be upward, and we can figure out how big that force is using our formula. It's a 5 amp current, 0.4 meter in length, 6 Tesla, and in this case the angle is 90 degrees. Multiplying that together gives a force of 12 newtons. Here we have a similar looking problem, but instead of the wire passing completely through the region of space where the magnetic field acts, it's forming this U. If we were to look at this wire, the current would be coming down the left side, as indicated, going across the bottom, and then back up and out the right side. And obviously there is more to this circuit than what is given here. Let's begin by thinking about the direction of the force on all 3 parts of the U. So we have the left side, the bottom side, and the right side. So for the left, fingers in the direction of the current, which is downward. The field is outward, therefore the force is to the left. On the bottom, the force is downward. And on the right, the force will be to the right. We can see that the force on the left-hand wire versus the right-hand wire are going to be in opposite directions, and therefore those two pieces will not contribute to the net force on the wire, and net force will be only downward. We can find the magnitude of the force on this wire. I don't know why I did that. Let's try again. Using our formula, ILB sine theta. The current is 3 amps. The length is 0.2 meters. The field is 4 Tesla. And the angle again is 90 degrees. Multiplying that together gives a force of 1.8 newtons. For our last example, we're going to calculate the force per length on this wire. Notice also I do give you the length, but it's not needed for the problem. Using the right-hand rule, we can determine that the force is out of the page. We can find the force per length using this version of the force on a current carrying wire formula. The current is 2 amps. The magnetic field is 4 Tesla. And now we need an angle. We look at the diagram and we see a label of 20 degrees. But remember that the angle theta that we need for our ILB sine theta formula isn't this angle, but this one. It's the angle between the magnetic field and the current. Since this is a 20-degree angle, that makes this a 70-degree angle. And that works out to be a force per length of 7.5 newtons per meter. If you put in the 0.2 meters for the length, this works out to be a force of 1.5 newtons. This concludes this portion of this unit. In the next part, we're actually going to quantify the magnetic field due to a wire and then do an example involving wires with either parallel or series currents.